Hi guys, in this video we will talk about Kirchhoff's voltage law, KVL, in circuits. It states that in a closed loop within an electrical circuit, the sum of the voltage rises must be equal to the sum of the voltage drops. In simpler terms, the total voltage around any closed loop in a circuit is equal to zero. Here's how you write KVL equations. Look at this circuit. It has two voltage sources, designated as V1 and V2, and three connected resistors, designated as R1, R2 and R3. The first step involves designating specific points in the circuit to identify loops, where these points represent locations where components connect. For this circuit, the designated points are A, B, C, D, E, and F. Next, is to identify the loop or closed path within the circuit for which you want to apply KVL. A loop is a path that starts and ends at the same point, passing through various circuit elements, like resistors and voltage sources, without revisiting any component. This circuit has three loops available for analysis. You can pick either a clockwise or counterclockwise direction. For example, we'll be using the clockwise direction. Initially, we can make the loop ABCDEF. Following that, we have the loops ABEF. And BCDE. Next step is to assign polarities to each component within the loop. For resistors, define a direction for the current flow. In this circuit, we have to assign the current direction entering R1, designated as I1, which follows this path, resulting in a polarity from the positive to the negative. Then, current entering R2 is assigned in this direction, resulting in a polarity from positive to negative, designated as I2. And for the assigned direction for the current flowing to R3, resulting in a polarity from positive to negative, designated as I3. For voltage sources, mark the positive and negative terminals. This step helps in keeping track of voltage polarities while going around the loop. So let's start writing our KVL equation for our circuit. First is to take the loop ABCDEF. At this loop, move in one direction, clockwise or counterclockwise, and add the voltage contributions across each circuit element encountered. In this case I choose a clockwise direction. Use the formula of voltage, which is V is equal to I times R for voltage drop across resistors and the defined voltage for voltage sources. To easily write the KVL equation, you have to use the sign of the ending polarity of the resistor and voltage source. Let's begin with V1. The polarity of the voltage source's ending, concerning the clockwise loop direction, is positive, so it's designated as positive V1. Moving on to R1, the current flow's ending polarity is negative, resulting in a notation of negative VR1. Conversely, for R3, the ending polarity indicates a positive VR3. Finally, V2 is labeled as negative since its ending polarity is negative. This equation will be set to 0 for further analysis. VR1 and VR3 can be written as I1, R1 and I3, R3. So the equation will be simplified as positive V1 minus I1, R1 plus I3, R3 minus V2 equal to 0. And substituting the values of resistors and voltage source, we have positive 10 minus I1 times 5 plus I3 times 2 minus 5 equal to 0. Adding similar terms of the equation, we have 10 minus 5, so 5 minus 5, I1 plus 2, I3 equal to 0. So that's it. This will be our KVL equation for loop ABCDEF. Moving on to the loop ABEF, the formulation is as follows. The equation starts with adding V1 and subtracting VR1 and VR2 to yield 0. Expressing it mathematically. Positive V1 minus VR1 minus VR2 equal to 0. Positive V1 minus I1 R1 minus I2 R2 equal to 0. Substituting the values of resistors and voltage source, we have positive 10 minus 5 I1 minus 3 I2 equal to 0. This equation represents loop ABEF. Finally, considering the loop BCDE. The equation starts with adding VR2 and VR3 and subtracting V2 to equal 0. Mathematically, positive VR2 plus VR3 minus V2 equal to 0. Positive I2 R2 plus I3 R3 minus V2 equal to 0. Substituting the values. Positive 3 I2 plus 2 I3 minus 5 equal to 0. This equation signifies loop BCDE. In conclusion, this demonstrates the process of formulating KVL equations for different loops within the circuit, providing a systematic approach to analyze the electrical properties and relationships within the circuit components.